So for next 2 hours, we will be kind of like focusing on the fundamentals of adsorption. So this is nothing to do with carbon dioxide in specific, but we actually deal with what is adsorption and what are the fundamentals and what are the things we have to look into the adsorption. So if you have done like BTech in chemical engineering, adsorption chapter, so some of the topics are covered in that one, but just for the sake of clarity, we kind of like also go through some of the fundamentals as well. Okay. So look at this one. This is like in the first 1 hour, we kind of like try to cover what is adsorption, what is the basis, how adsorption happens, what kind of like things we have to consider. And the second one, coming to the adsorbents, what are the existing adsorbents, what are their characteristics, what exactly we wanted as a perfect adsorbent, right? And so there may be so many adsorbents available in the market, but some of them are industrially useful. So why these adsorbents are industrially useful? What are those characteristics? So we will actually go through those paths, and then finally we kind of like talk about adsorption equilibria, like different types of adsorption isotherms. Especially, it is nothing to do with the models. That means that we don't talk about Langmuir model or BET model or Friendlich model or whatever. We kind of like talk about what are the characteristics of an isotherm, right? So those things we will talk about here in the first 1 hour. So you all may know that what is adsorption, right? What is adsorption? Right? So adsorption is ability of certain solids to kind of like adsorb or to some of the components, one or more components. It's like not just one, it may be more components from a liquid or gas mixture, right? So it's not only for the gases, although here we kind of like specifically talk about gas adsorption. Adsorption can also happen with the liquids. So some of the components can be adsorbed from the liquid solution to the solid. So anything when an adsorbate, here we see here, oh yeah, sick, sorry. So here, this is the process adsorption. So the solid, we call it as adsorbent. So whenever I say adsorbent, that is solid. And adsorbate is either gas or liquid, most likely gas in this case. Okay. So this process we kind of like most likely use in industry, kind of like removal of moisture. So that means that water vapor, to remove water vapor is kind of like you put a solid, you kind of like try to absorb those water molecules onto the solid surface, and the other gases is like moisture free. So this is because when we have like moisture in the stream, it's like the system is probed to corrosion happens. So that's why we have to remove the water. So the most of the cases, that's what they do. But the same process, yeah, same process can be used to separate the gases, especially some of the gas mixtures like xylene, methane, ethane, propane, nitrogen, and so on and so forth. Because to separate some of these gases using the existing techniques like distillation or absorption, which is it's kind of like these are energy intensive operations as well as they are actually like very costly. So that's why we kind of like use adsorption in that case. So let's go to the basic difference. Maybe you kind of like have a thing into your mind. So always remember absorption and adsorption are two different processes. So these two things together, some people call it as sorption. When you say sorption, it can be absorption or adsorption, right? But these two are not same, right? So whenever you talk about absorption, that is like something to do with the bulk. And when you say adsorption, AD, that is something to do with the surface. Okay. So although there are like so many differences which you can go through it, which I will not go through each one by one. One thing I kind of like want to tell you that whenever we talk about adsorption, note that it's a surface process. It's not a bulk process. So like look at this one. This is the only thing I want to tell you. So the one which you see here, this is the one. So this is the adsorbate, right? So whenever adsorption is happening, so the one you can see here, right? So this only, we are only talking about the surface process here. Nothing enters into the bulk of the thing. Whenever you talk about the absorption, it is kind of like a mix. It's a bulk process, right? So although you see here, this is adsorption, this is absorption. Just put it like that. Right. So this one, When it comes to the adsorption, right, so we kind of like focus on the adsorption, then we can see that there are two types of adsorptions. One is physical adsorption, so that only deals with the van der Waals interaction. And you say chemical adsorption, which kind of like whenever there involves a van der Waals bond, like sorry, a covalent bond, right? So whenever we talk about chemical adsorption, we are talking about something to do with the bonds. Whenever we talk about the physical adsorption, we talk about the van der Waals interaction. That means that there is only attraction between the surface and the molecules. So that's why they come and absorb onto the surface, but there is no chemical bond involved in this case. It's muted. So whenever we talk about physical adsorption, one thing you all remember, this is a reversible process. That means that the adsorbed molecule will kind of like again go back. That process can, then the process is called desorption, so which we most likely don't deal with it. And whenever we say chemical adsorption, we say it's irreversible process because the bond have formed. So it is not fully irreversible in most of the cases. And heat and all, we will talk about the heats whenever a gas molecule adsorb onto the surface, what kind of heat will be released and how much the heat and what to do with this heat. This all we will deal with the thermodynamics of adsorption, which will come tomorrow. So we only like in this today, like maybe in this lecture and the next lecture, we will only talk about the physical parts of the adsorption. Tomorrow we talk about the thermodynamics of the adsorption. Okay. So when it comes to the adsorption, this is the very important thing. Adsorption, whenever we say adsorption happened, a separation happened, it may be because of the three reasons. So one is the steric interactions. So steric interactions means that you have a solid surface which is adsorbent like this, right? So this is the pore structure which may be available in adsorbent, something when you look at the nanoscale, right? So whenever you have two gases, so one is a small molecule and one is a very big molecule, something like this. So this pores only allows small molecules to go through it. So only this molecule will go through it, and this big molecule will not go through it. Right? So that is called, this process still we call it as adsorption, but it's something to do with the steric thing. Okay. Second one is equilibrium, which we most likely we do see. So what happens is that, so whenever you have an adsorbent something like this, you have two molecules, so which both can go through it, but this surface adsorbs this molecule more than this molecule. That means that interaction between the surface versus this molecule is more compared to interaction between surface with this molecule. So then what happens is that whenever this attracts more, so this will go and sit into the pore surface, and this molecule, less molecules will go and sit into the surface. So that is second kind of separation can happen, that's called equilibrium. So third one is called kinetic mechanism. So kinetic mechanism, which we kind of like see, so you have like two molecules. Yeah, this one, they both are same. So this pore structure can accommodate both the molecules. Right. One is this, maybe one is this. So both can enter into the pore surface, but this can diffuse faster and this diffuses slower because of several reasons. One may be the size, two may be the interactions, right? So what I mean to say is that maybe if this molecule is strongly attracted to the surface, this molecule will not diffuse faster because it is strongly attached to the surface, right? So even though the gas molecules have more adsorption capacity, sometimes it may be kind of like in terms of kinetic mechanism, it is not good for it. Okay, so these things we will see maybe sometime tomorrow when we discuss about the diffusion resistances. But the third one is the kinetic mechanism, that is because of the diffusion rate, how fast a molecule can enter into the system. Okay. So as I said, adsorption is a surface phenomena, but why we are talking about entering into the pore structure, right? So do you ever think like that? We are saying that adsorption is a surface phenomena, so that means that it should happen just on the surface, not into the bulk. But why we are talking about all these things in adsorption, right? So it is still on the surface, but surface of the pore, right? So it will not enter into the bulk core part of the system. So here it will not enter. So it just enters through this one, which is still the surface, and leaves it. Okay, so that is the only thing. Right. And the next one. So we will kind of like go through one by one. So as the situation comes. Go. So like first we will focus on the adsorbents. So that means the solid. So what are the characteristics of the solid we wanted, so that we kind of like adsorption is happens in a way we want it. Okay. So usually how we will use this adsorbents is that we kind of like use this like in the form of small pellets, right, or in terms of beads, or in terms of like granular forms. We kind of like split these solid adsorbents into these forms and put it into a packed bed or anywhere in an adsorption setup, and then we will use it. So usually these are of in the size of 0.1 mm to 12 mm size. So it means that these adsorbent materials is kind of like, you say this is the adsorbent. So this is in the order of 0.1 to like 12 mm size, right? But that will come. Okay, so these are the things. But when, well, like what size we should use, whether we should use 0.11 size or 12 mm size, it all depends on the system to system. So again, which we will kind of like comes into thermodynamics, how we have to choose these things, right? We need to kind of like make sure these things have been taken care of. If the particle is so big, right, so then what happens is that it will offer a lot of resistance, because the gas molecules has to flow through this one, right? If gas molecule, if the adsorbent molecule is so thin, like say if you use 0.1 mm, so then what happens is that it will offer more pressure drop to the gases, and it will not have adequate strength. So we kind of like have to take care of all these things when we design an adsorbent column. So we kind of like have to take care of all these things and then choose the proper adsorbent material. And then second one, once we kind of like take care of all these things, the thing we have to look into is adsorptive ability. That means that this material, solid material, how much it can adsorb, right? So which is very important thing. So if you kind of like take care of everything, like okay, so you take care of the size, you take care of the shape, you take care of the bed, but still it does not absorb the gases, so it does not good. So that's why we kind of like, first we kind of like take care of the sizes and all, and then second we will look into the adsorptive ability. So how much it can adsorb, okay? So third one is highly porous. We want a porous material. If it is highly porous, it can accommodate more gas molecules into the system. So then the fourth one is large surface area per unit weight. So whenever for a unit weight you have large surface area, that means that a lot of molecules can go and sit onto the surface, because it's a surface phenomena. Okay. So look into the surface area and then pore size distributions, how it will affect, right? So the first one is the surface area. If you have more surface area, so the dissolution rates are very high, adsorption capacity is very high, and whenever the surface area very high, so it represents surface free energy available. That means that more free energy is available. So then whenever there is a chemisorption, so it is good for chemisorption, because the bonds can be easily formed when the surface free energy is very high. Okay. So second one is pore size distribution. So we kind of like have to take care of pore size. So this is the adsorbent size, right? So whatever we say 0.1 mm to 12 mm is the size of the adsorbent, right? Inside this adsorbent, what is the pores? like how big these pores are. So these pores are very small, like that, or very big, something like this, or like what kind of pores are available. It's maybe straight channel, something like this, or a zigzag channel, something like this, right? So all these things matters. So that's why we also have to look into the pore size distribution, what kind of pores are there, right? So sometimes when we kind of like do the analysis, it says that large pores are available. So whenever you see here, so some pores looks like this, right? So some pores looks like this. So whenever you do the pore size analysis, it says that okay, big pores are available in the system. So that means that it actually sees here. So here you can fit a very big molecule. So it says that oh, okay, when you do the analysis, it says that okay, large pores are available. So this much big molecule can enter into the system. But it is not true. Actually, you can fit one molecule here, but if it travels from this place to this place, it has to go through a limiting pore size, which is here, the smaller one. So it will kind of like obstruct the flow of this molecule from one pore to the another pore. So we kind of like have to check what is the pore size distribution. What is the biggest size of the pore? What is the smallest size of the pore? So we need to cross check everything before selecting these materials. So that's what we kind of like talking about diffusion rates. This molecular sieving properties is like this, which kind of like does not allow. And we also have to look about, always we will look into surface area per unit volume, because that's what we wanted. More surface area we wanted for adsorption. Okay. So as per IUPAC classification, pores are divided into three types. The micropores, which is the diameter less than 2 nanometers, that means 20 angstroms. Mesopores, which is between 2 and 50 nanometers, and any pores bigger than 50 nanometers is called macropores, right? Whenever we deal with small gas molecules like CO2, we always deal with microporous material. So because CO2 size is roughly like 4 angstroms, right? So we should kind of like choose which is around like 4 to 10 angstroms. If you choose a bigger one, it makes no sense because it allows everything else. So whenever we kind of like want to capture a CO2 molecule, we kind of like deal with pores which is around 1 nanometer or less than 1 nanometer. Okay. And these are the different types of the pores available. So some pores are like smooth, something like this. Oh, sorry. So what you can see here is that some pores are very smooth, and here some pores are like zigzag, and here you see some pores are like having like large pore sizes followed by small ones. So this is called cage type pores, right? It's kind of like a cage. It will allow you to enter into the first one, but it will not allow you to flow through it. So it's kind of like a cage thing, right? So we talk about three different types of pores, and in terms of size, we also talk about three different pores in terms of surface. So that means this is smooth pores, this is zigzag, and this is cage. Okay. Yeah, let's go. So why do you think it matters, right? You just see one example, right? So what has been done here is that you see the same material, which is silica gel, so that is adsorbent, right? So they kind of like created same with the help of same material, but different pore shapes. Sorry, yeah. So different pore diameters. So here they have pore diameters of 2.1 nanometer. Here you have see the pore diameters of 3.3 nanometers. And we will talk about adsorption isotherms later, but just look at this one here. On the x-axis you have pressure, on the y-axis you have the uptake, that means amount adsorbed. You see the amount adsorbed in both the cases are different, depends on the pressure. So what happens is that when the pore sizes are smaller, which is 2.1 nanometers, what you see here, right? So at low pressures, it adsorbs more number of gas molecules compared to this one. But when you see at higher pressures, so the one which is having high diameter or higher bigger pores is adsorbing more. So we will see why this is the case. Okay, so why there is a transition at low pressures, why this is performing better, at high pressure why this is performing better. Okay. Right. So I will not go through it, it's just for the information. So there are several adsorbent materials are available. So they all are like tested either at the lab scale or at the industry level to kind of like separate the gases or water vapor and so on and so forth. So especially nowadays, most of the people are kind of like working on the molecular sieves, which is like geolites, metal organic frameworks, covalent organic frameworks, which we will go through it. And yeah, so especially if in the industry, the mostly they will use kind of like to separate the water vapor from a gas mixture. So they use alumina thing. So this is because that it is very easy to kind of like functionalize the alumina. So when you functionalize alumina, which kind of like adsorb the water molecules, because water is a polar molecule. So alumina is one good choice. The second one is the silica gel. Silica gel itself kind of like can attract the polar molecules, and it has high surface area compared to the alumina. So silica gel is one of the option that is available for especially separating the water from the gases, right? And then third one, which we kind of like fully explored, is activated carbons. So activated carbons will have different structures, depends on the nature of synthesis, how you synthesize the material and so on and so forth. So it will have extremely high surface area, high micropore volume, and it is used to separate the gases, even the bigger gas molecules like xylene and so on and so forth. And nowadays people are kind of like using geolites. So geolites are kind of like industrially using to kind of like separate the gases and water and separating some pollutants from the water as well. So these geolites are of two types. One is naturally available, one is kind of synthetic geolites. So most likely for the gas separation we use synthetic geolites of different sizes and shapes, which has been shown here. So the new generation of materials which people kind of like trying to explore, these materials are not industrially kind of like explored. It is still in under academic exploration stage on. So one is the metal organic framework. This is like also like geolites, but thing is that it has a metal node connected by a organic linker. So how many linker molecules we have, how many metal molecules we have, and so on and so forth, it can actually form different structures as you can see here, right? So different sizes, different shapes, and so on and so forth, and these are actually flexible molecules unlike geolites. So geolites pore structure is well defined, so most likely it's a kind of like crystal, so the pore sizes are almost same at all the time. But what happens with the metal organic framework is that when the gas molecule enter into the system, this metal organic framework either try to compress or expand depending on the interaction between the gas and the MOF materials. And they are flexible systems such a way that when I say pore structure looks like this, but this is kind of like flexible. That means that this kind of like expand and contract all the time. So it kind of like allows the gas molecules to enter into the system. So then next, so this is kind of like you can see that what happens in gas adsorption in terms of MOFs. We are not talking about adsorption isotherms a lot because we did not discuss what is an isotherm, but as you can see here that this MOF material can adsorb CO2 a lot compared to any other gases. So whenever you put a MOF into a system consisting of different gases like CO2, CO, N2 and H2, it can kind of like only adsorb CO2 molecules and separate CO2 from all other gases, right? So the next class of materials people now trying to explore is covalent organic frameworks. So it is similar to metal organic frameworks, the covalent organic frameworks will not have any metal. So it is connected by a covalent bond. So all the linker molecules are connected through a covalent bond and forms a well-defined structure. As you can see here, the structures are very well defined, and yeah. So then next class of materials, which is just coming up, maybe a couple of people are explored so far for the gas separation, especially for CO2, is that flexible hydrogen bonded organic frameworks, right? So the difference between these three classes is that so when I say MOF, you have a metal and then it's connected through an organic linker and then another metal. So it's like this, just giving one example, right? So it's a very well defined structure, something like this. Whenever we say covalent organic framework, we will not have any metals here, right? So these linker molecules are connected through, these organic linker molecules are connected through another covalent bond. So that is covalent organic framework. Whenever we say hydrogen bonded, this one, so they are not connected by a covalent bond, they are just connected by a hydrogen bond. So physically there is no bond, but only if hydrogen bond exists. So these materials are showing very good performance for the gas separation. You can see even like molecules of similar size, C2H2 and C2H4, right? It is only taking C2H2, it is absorbing C2H2 but not C2H4, although both have similar size, right? So these are the new generation materials that are coming up now, right? So now talk about adsorption equilibria. So what is equilibria? Rate of adsorption is equivalent to rate of desorption, then it reaches an equilibrium. Yeah. So whenever you have a surface, that is, you have an adsorbate material, right? So then it's kind of like allow sufficient time to interact with an adsorbent molecule, right? So then what happens after some time, the rate of adsorption is equivalent to the rate of desorption, and then we kind of like can say that we reached an equilibrium stage, right? So like that at different pressures we try to kind of like understand how much it adsorbed, that come on, yeah. So that we can kind of like call it as an adsorption isotherm. That means that at 100 bar pressure, at 100 mmHg pressure, so how much it adsorbed at 0 degrees. So for example, you see here it's around 60. So at 200 you measure, 300 you measure, 400 you measure, and then you draw all the points on pressure versus amount adsorbed. That's what we call it as adsorption isotherm. So because we are calling it as an isotherm, it is because it is all the measurements are happening at constant temperature. So this adsorption isotherms depends on the temperature. Okay, that's good. What else? Yeah. So coming to the adsorption mechanisms. So whenever we say adsorption happened, it can happen in three ways. So one is monolayer adsorption. That means that whenever we have a surface, the gas molecules will only adsorb on the surface. Okay. So that means only one layer of gas molecules can adsorb on the surface. So that's called, we call it as monolayer adsorption. So whenever we say multi-layer, that means that still there is a surface. So then monolayer adsorption happens. On top of those gas molecules, another gas molecule will come and adsorb. So this is second layer and that is third layer. So this is called multi-layer adsorption. So last one which we kind of like talk about is the capillary condensation. So this happens a kind of like a pore. So for example, you see this is a surface here. So this is a surface here. So here monolayer adsorption happens. On top of which you see here second layer of adsorption happens. So then the pore becomes like a small one. So where the gas molecules condense and forms like a liquid, right? So this is kind of like called capillary condensation. So this is a third type of mechanism that can happen in any adsorption process. Okay. So whenever we kind of like try to see a adsorption isotherm, based on the adsorption isotherm, we can say that what kind of adsorption happens. So that is the thing. Oh yeah, okay. So that's the thing, we will kind of like go through it. Like, so when monolayer adsorption happens, how the isotherm looks like. When a multi-layer adsorption happens, how an isotherm looks like. When capillary condensation happens, how an isotherm looks like. That's what we kind of like discuss in next few minutes. So this is a simple slide where it actually shows, like whenever you have a pore something like this. So this one here you see, this is a monolayer adsorption. So here you see it's a multi-layer adsorption, you can clearly see. And then where you see here, so a monolayer adsorption followed by capillary condensation. Okay. So let's look at the type 1 adsorption isotherm. So there are 6 types of adsorption isotherms, so which we will kind of like look into. So the first one is type 1. What do you observe here? So here, although I did not mention here, the x-axis is the pressure, y-axis is the amount adsorbed. What you do see here? So this is kind of like I have both adsorption isotherm and desorption isotherm. So both looks like that. So that means they follow exactly the same path. So what are the characteristics of type 1? You see that this is a pressure axis, right? And this is amount adsorbed. Even at low pressure, right? So just low pressure, the amount adsorbed increases exponentially, right? So it reaches equilibrium very easily. Look at the characteristics. So one, look at the curve type. It's a concave to pressure axis, which you can see. So this kind of like process happens typically in micropores. That means less than 2 nanometers. So adsorption proceeds at best up to the formation of the monolayer. So it means that, so it's a monolayer adsorption happens. So that means that when the surface is there, it's only one layer it forms. So this is good for solutes that present in low concentration. Okay. Why? Because only monolayer adsorption happens. That means that amount it can adsorb is kind of like limited. So as long as the surface is available, it will adsorb, otherwise it will not adsorb. So in that case, we kind of like, it's good for solutes that present in low concentrations. And what you see here is that relatively high solute loading at low pressure. So at very low pressures, it kind of like adsorb a lot of gases. So these are the characteristics of type 1. Let's go to the type 2. So here also, as you see, adsorption and desorption follows the same path. But what you can see here is that a knee kind of structure. So like this with an inflection point somewhere here, right? So that means that this is a characteristics of multi-layer adsorption. So then what happens is that when you kind of like have a, oh my god, always I use. Right, maybe I will write like this. Right, so you have a surface like this. So at low pressure, so the gas molecules will come and sit on the surface, something like this. Okay, so that's where from starting from here, it will go until here. So after this point, then the gas molecule started sitting on this. So that's why as the pressure increases, so the adsorption may happen something like this. So that's why as the pressure increases, the uptake increases. So this is like first layer and then go on. So it is most likely a multi-layer adsorption happens here. And then second thing, you see this, whenever you observe something like this, it only because of the physical adsorption. This is because in multilayer adsorption, in chemisorption, multilayer will not happen because a bond should form between a gas molecule onto the surface. So it can only form bond here, but not from here. Okay. So whenever there is a multilayer adsorption, most likely it's a physisorption. So this is type 2. Okay, let's go to type 3. What type 3 says? So again the same one, adsorption and desorption follows the same path. So anyhow, the shape, the first one talks about the convex to the pressure axis. This happens when the gas molecules strongly interact with the gas molecules rather than the solid surface. That means that when you have an interaction between gas and gas, and you have interaction between gas and solid, right? So first one here, second one here. So what happens at the low pressure, right? So when you say nothing is here, just solid surface is there. What we are saying is that gas-gas interactions are greater than the gas-solid interactions. So that means that these gas molecules like as you increase the pressure, it slowly kind of like come and sit on the surface, something like this. So that's why as the pressure increases, it slowly increases the uptake. Once the gas molecules come and sit, then it's started like, because gas-gas interactions are stronger, they will start like building on one another, right? So this kind of adsorption happens when gas-gas interactions are stronger than the gas-solid interactions. So that's why initially it is pretty slow, after that it increases exponentially. Oopsie. Right. Coming to the type 4. So here is the first time what we are seeing is that adsorption isotherm is not following the desorption isotherm. So there is a change in between somewhere. So this is kind of like happens whenever there is a capillary condensation. So when a gas molecules, like whenever there is a capillary condensation, what happens is that these gas molecules condense into the liquid. So it requires more energy to convert liquid into the gas. So that's why it does not follow the same path, it follows a different path. Okay. And then second thing what you see is like alternative things. So that means this is monolayer, second layer, third layer, and so on and so forth. So type 5 is exactly same as type 4. That means that adsorption and desorption does not follow the same path. But this happens when gas-gas interactions are stronger than the gas-solid interactions, right? It is exactly like what you can see is that type 4 is actually equivalent to type 2 with capillary condensation, and type 5 is equivalent to type 3 with capillary condensation. Okay? So that's what you see here. So one thing we all have to understand from all these things is that whenever adsorption isotherm and desorption isotherm does not follow the same path, that means that capillary condensation is involved. Okay, that is one thing which. Okay, type 6 is a very good one. It's like a very good student. So what happens is that in type 6 adsorption isotherm, so the gas molecules kind of like follow a same pattern. So this happens when the solid surface is uniform. That means that first the gas molecules will try to fill all the surface pores, that is here. So that means from here to here a monolayer will form, then it start filling the second layer. So like this. Once the second layer is done, then only third layer. So that's what you can see, first one, second one, third one, and fourth one. I'll just show you one example where we get this one. Oh, hey, look at this one. So this is adsorption of krypton on graphite surface. Look at this one, how it actually happens. So there is a peak, that means that all the krypton molecules are sitting on the graphite surface. Once the first layer is full, and then like slowly it goes to the second layer and then third layer. Okay. So these are the 6 types of adsorption isotherms which we kind of like talk about. Whenever we see these adsorption isotherms, we can actually come back and say like, okay, what kind of a process or mechanism happening in the adsorption, whether it's a multi-layer adsorption or monolayer adsorption or capillary condensation is involved, or it forms layer by layer. So look at the adsorption isotherm and go back to the mechanism and see how it is happening. Okay. So any questions? So anyone from online? Right. That's good. Oh yeah, sure. Yeah. Metal organic frameworks. Usually, whenever we deal with gas molecules, that it's still at the lab stage only. Whenever we do these things, adsorption and desorption follows the same pattern because most likely capillary condensation may not happen. So, but however, it depends on the system to system. So, whenever you kind of like try to separate CO2, methane, and so on and so forth, small gases, water vapor, using metal organic frameworks. So, adsorption and desorption follows the same pattern. Yeah, so.
In our air separation plant, we use molecular sieves for adsorption. It's okay if I say.
Yeah, okay.
Yeah, in our air separation plant, we use molecular sieves for adsorbing CO2.
Okay.
There, we are using nitrogen for the case of desorption.
Desorption.
Yes.
Okay. No.
That way, do we require any other medium for the desorption part of when we deal with metal organic frameworks?
Like I mean to say, when you adsorb it, you are adsorbing CO2, right?
Yeah, from air, whatever CO2 is present in the air, that
Okay,
is
you
being
are
adsorbed
okay,
using
and
molecular
then
sieves.
okay, and then like whatever nitrogen also adsorbed, you try to
No,
dissolve.
no, no. For the case of desorption, we will be sending nitrogen in the opposite direction,
Okay, so that it
which will remove the trapped carbon dioxide from the molecular sieves. In same way, if we use metal organic frameworks as the adsorbent material, what will be the medium used for desorption purpose?
So during the purging, I guess you are talking.
Yes, yes, sir. Because it is cyclic.
Yeah, we generally use any inert gas. Okay, that should not adsorb in the either metal organic framework or the zeolite. Okay, by the time it would whatever the adsorbent that is present in the gas phase, that will come out during the purging phase.
Mm-hmm.
Okay, that's how it could be.
So any inert gas like a nitrogen or a
Yes, we
will be sufficient with metal organic frameworks
mostly we
also.
use nitrogen.
Yeah.
That is most available.
Yes, yes, sir.
Two gases, it comes with CO.
Mm-hmm. Okay.
yeah, okay, purging. Yeah.
So here in adsorption capacity different from layer to layer also.
Adsorption capacity depends. Yes, it depends on layer to layer. Yeah.
But how, because the interactions are between the layer, probably absorption capacity is varying with the structure of the layer. You see the surface, the absorption is happening, it is increasing.
Right.
But after that, the next layer it comes, it just saturates. Then again it increases. Because the interactions are between layers, it is not between the surface and the layer.
Yes, but no. Okay, so what you're talking is here, right?
In this one only, type 6.
Okay. So here what happens, here the gas molecules are interacting with the surface first.
Yeah.
Right? So then it's like, then the second layer starts.
Yeah.
So this is the second layer of adsorption. Okay. So until it kind of like reaches that full second layer adsorption, so it kind of like, you see, this follows a similar trend. I mean to say the adsorption capacity is almost same because it forms on the first layer only.
No, my question was actually with respect to type 6. Can you go to the slide 26?
Oh, stop.
Type 6, yeah.
Okay.
So, yeah, so in this case, the first increase from 0 to 1 is because of the interaction between the surface and the gas molecule.
Surface and the gas molecules.
Now
Yes.
the first layer is absorbed, which
Yes.
we call it as monolayer.
Yes.
The next layer is going to come up, which is going to get absorbed on the first layer.
First layer of the.
So there the adsorption capacity is nearly saturated. It stays around 1. It
No,
stays around 1.
you can see this one, right? See, okay, you are following this one or this
Yeah,
one.
yeah.
You see, here it goes from 0 to 1,
Yeah.
right? So second one is kind of like say 0.8 or whatever.
This which is staying around 1. This is like on the monolayer. The adsorbates which are going to get absorbed on the first layer.
First layer, right?
Now this first layer is done.
Okay.
And this second layer is also done, which is around 1. Now the third layer is going to come up, wherein we are seeing a high uptake between 1 and 2. So why this jump between the layers?
No, wait. See, let me tell you. So this is the first one you understand, right? This
Yeah.
is between the gas and the solid.
Yeah.
You just look at this one.
Yes.
So from here,
Is the gas to gas?
like here is like gas to gas,
Okay.
right?
Okay.
And this is gas to gas. Here there is no adsorption. You see this, like as the
Yeah,
pressure increases,
okay.
there is no adsorption happening here,
Okay.
right?
Okay. There is no adsorption.
No adsorption, right? So you kind of like have to increase the pressure so that the gas-gas adsorption starts happening.
Yeah.
So then after this second layer, this is third layer.
So this is limited by the partial pressure also, because you have to operate around 0.4.
Obviously, yes. So okay, you are talking about this is gas-gas. No,
Yeah,
that
yeah.
is not the one.
Can you go to slide 23?
Slide 23, yeah.
So what about heat of adsorption in this particular case?
No, we'll talk about heat of adsorption when it goes to the thermodynamics. We'll go and discuss each case.
And in type 2, you mentioned about non-porous powders, that type 2 is preferred in non-porous powders.
Type 2? Yeah.
One of your points say that.
Yeah.
The second one, the most frequently found when adsorption occurs in non-porous powders.
Non-porous
What
powders.
do you mean by that?
So what happens here in type 2? So here, like you see here at low pressures, so the gas try to adsorb here, right?
Yes,
That means
yes,
that
sir.
solid gas interactions are very high.
Yes,
So it's like peak is there, right?
Yes, sir.
So whenever you have like a non-porous powder,
Okay.
so that means that adsorption only happens on the surface,
Okay.
right? It's not like porous. Unlike, so it only happens on the surface, somewhere here. So it adsorbs initially here, and then slowly it goes. So this is kind of like multi-layer.
Should that portion that you are entering in type 2 to the lower pressure conditions, would that reflect microporous conditions also?
Microporous, sometimes it can, yes. But you mean to say this much? No, when it's a microporous, right? In between micro and meso. Oh, why do you think so?
No, just like there are two.
Yeah.
There are two patterns that are being reflected here, like type 2's part, type 1's part, and as well as actually type 3's part. Because like in the higher pressure conditions, we are actually having an inflection.
Inflection,
That's
right.
happening. The same thing actually in type 1's part, actually we are actually having a micro. At
Yeah,
low partial
initially when-
pressures, you are actually.
yeah,
So
absorbing more.
won't that be a combination of intermixing of both microporous
And mesoporous
combination?
Okay, so so most likely this happens in non-porous powders. Like why we are saying is that, like what you say is that is a sharp uptake is there, so that's why it can be microporous, which we are referring to. So when you say it's a microporous, right? So that means that so some pores are available inside. So it's try to fill everything here, right? Right. So say for example, it's a microporous now, and the second one is that after this point, now all the pores are filled. So still the gas adsorption is there. So where it is coming from?
So that should be actually between gas-gas interactions, right?
Right. So that means that you mean to say it's kind of like coming in somewhere in between.
Yes.
So whenever there is kind of like somewhere in between these gas molecules are adsorbing, then the condensation do happen. So then this does not follow the same path. So because that hysteresis is not there, which we kind of like talk later. So now we can say that, okay, so these gas molecules are not kind of like coming in between. So there is no condensation happens.
So, but it will also depend upon the pore size distribution parts also.
Right. So it also depends on the, like, yeah, if you have a bigger pore, something like this, right? Yeah. Oh, right. So maybe one layer, one layer, one layer, one layer. Even after some time, so the condensation should happens. So it is not happening at least until we reach the saturation. So that's why we kind of like, but still it can happen. Like if it is like, it's a huge thing, like say in between 2 to 50 nanometers. So if we kind of like don't go into the condensation region, yeah, it can happen. But it most likely happens. That's like most frequently found. It's not that
Because
always
like,
found.
MOFs usually have similar patterns like this.
Yes, it's do, right. I agree. So especially in MOFs, whenever you see these things, you also like experimentally also you see the condensation also. Like condensation do happens. Like I mean to say, you see the hysteresis loop in MOFs.
That is too narrow.
Yeah, the too narrow, right. Yeah, because we are not going to that far. Like in MOFs, usually the pores are of 2, like I don't know, even 2 nanometers is big. 1 nanometer only we have, but yeah, that's true.
So there is one question from online participants. It is just now, I think Professor Ravi answered. It is regarding in MOFs and CAFs, which type of adsorption happens, and what about amine functionalized MOFs?
Okay. So this functionalization and all we will come back, like we will do it. We have like a class tomorrow which we kind of like discuss about the diffusion and then the effect of functionalization. That time we kind of like, yeah, try to discuss thoroughly about the functionalization. And yeah, so anyhow, I think we kind of like have discussed what kind of adsorption happens in MOFs. Is that usually we observe type 2 in MOFs as well, because it's kind of like monolayer adsorption do happen on MOFs.
So, and also it is better we classify these isotherms based on the pore size, like as Professor Ravi was telling, microporous, mesoporous, and macroporous. Because MOFs, there are MOFs and CAFs which may belong to either mesoporous and microporous also. So it is always concentrating on the pore size.
Pore size.
Based on pore size, you can classify them.
Yeah,
Okay.
rather than the type of material.
Yeah, that is better. Please continue.
Okay. Any other questions?